Hey guys, what's happening? Anyway, all right, so 4 episodes in. This is usually the time of the semester, if you're actually watching these in order week to week. Either way, odds are you're probably watching this around the time you're having to take your first exam for Chem 1 or Chem 2. And yeah, I guess I'll say more about that next week, because at this point, I guess it depends on what you've been doing the last 4 or so weeks. If you're trying to watch every video you can find on YouTube right now, hoping for some magic spark, and you got to take the test tomorrow morning, you might have what we in the education field call, you're about to have what we in the education field call a teachable moment. But I might talk about that a little bit more next time for the lead in. All right, so also, hopefully the show sounds better because I got a mic. And if you want to know, I tested it out and it sounds a lot better. If you haven't heard the last ones recently, all right, this is what it sounds like with the mic. And this is what it sounds like with the webcam mic. So yeah, webcam mic, collar mic. Sounds a lot better, doesn't it? All right, so I am almost a real show. Now all I have to do is find a way to get a picture in the picture, but we'll do that next week. Anyway, so what we're going to do first for General 1, we're going to talk a little bit about percent composition and how you can figure out empirical formula based on given percentages. So let's, oops. All right, so to start with, let's say you have a compound. And it's 35.6% nitrogen and 64.4% chlorine. So with that bit of info, you should be able to figure out the empirical formula. So to go from percentages to the empirical formula, you basically have to follow the same 3 steps. That first step is to convert your percents to masses in grams. And the way we can do that is we can pretend we have a 100-gram sample. Now you can pick any mass you want and it would work fine. You'd still get the same answer by the time we get to the last step. But since percents are based out of 100%, it just makes the math easier. Instead of having to find 35.6% of some number, we can just say 35.6% of 100, that's 35.6. So this compound is, for a 100-gram sample, it's going to have 35.6 grams of nitrogen, or nickel, I'm sorry. Can't read my own handwriting. 35.6 grams of nickel and 64.4 grams of chlorine. All right, so now that you have your 2 elements in a mass unit, now we can convert that mass to an amount in moles. Because whatever the subscripts are in this nickel chlorine compound, that ratio of X to Y, it's a numeric ratio. If we here in grams, that's a mass. Oh, those are masses. You divide the 2, you're going to get a mass ratio. We need to figure out the numeric ratio, And moles is a numeric unit. It's a counting unit. So remember, the way you go between grams and moles is use the molar mass of that compound. So nickel's molar mass is 58.69. Which gives us 0.607 moles of nickel. And if we do the same thing with chlorine, we get 35 point, or use chlorine's molar mass of 35.45. I was jumping ahead, but reading what I have there. So yeah, converting grams to moles using chlorine's molar mass gives us 1.82 moles of chlorine. All right, so we know we have 1.82 moles of chlorine. Oh, it keeps disappearing on me. For every 0.607 moles of nickel. So this will allow us to finally get the formula in our last step by taking those moles and getting a ratio. And the easiest way to get a ratio is to divide both by the smallest. So you take 1.82 divided by 0.6. Oh, I don't know why it keeps disappearing on me. There we go. 0.607. That will give you 2.99. I think I just hold it down, which is really, really close to 3. And just to be complete, we can divide 0.607 by itself to give us 1. So it gives us 3 chlorines for every 1 nickel. Put the 2 together, you get a ratio of 3:1. So it looks like our empirical formula is NiCl3. So again, stepwise, what we did was we converted our percents to grams. And if we use a 100-gram sample, it's really just a matter of changing the percent unit, the percent sign to the letter G. Then we use our molar mass to convert those grams to moles. And finally, that'll allow us to divide all of our numbers by the smallest to give us a ratio. All right, so let's try another one. And in this example, we've got a compound that's 43.6% phosphorus and 56.4% oxygen. And again, what we're going to try to do here is figure out the empirical formula. So again, step 1, convert percents to grams, which would give us 40. If we use a 100-gram sample, that would be 43.6 grams of phosphorus and 56.4 grams of oxygen. Next, convert grams to moles using each element's molar mass. So phosphorus's molar mass is 30.97. And that will give us 1.41 moles. And 56.4 grams of oxygen divided by its molar mass of 16 gives us 3.5. Thought I was reading the wrong line there for a minute. 3.53 actually. So again, we divide each number by the smallest. So we would divide 3.53 by 1.41, and that will give us 2.5. Now, in the previous example, we had the number 2.99, and we rounded that to 3. We said, yeah, I was close enough to 3. That's okay. Taking 2.55 and rounding it to 3 is not okay. You don't want to do that. Because one of the shortcomings of this system is, these steps is that when you get to the last step, you're dividing everybody by the smallest number. So by default, your ratio is going to be something to 1. But not every ratio is something to 1. You can have a 3-to-2 ratio, or 5-to-2 ratio, 7-to-3, any other things that are besides something to 1. But again, when you divide by the smallest, it's always going to be 2-1. But the way you watch out for these other types of ratios is you see if you can spot a fraction in your number. So 2.5, that's 2.5. So the ratio isn't, 3 oxygens to 1 phosphorus. Guys, again, that was oxygen, that was phosphorus. It's 1 phosphorus to every, or 2.5 oxygens to every 1 phosphorus. So always be on the lookout for fractions, because you don't round away fractions. You have to basically multiply them away. And whatever the denominator is, you got to multiply your formula by that. So 2.5 to 1 multiplied up to whole numbers would be 5-to-2. And that's our empirical formula, P2O5. So again, be on the lookout for fractions. So, if it ends in 0.5, that's a half. If it ends in 0.33, that's a third, etc. And there's an easy way to check your work. There's lots of easy ways to check your work in chemistry, so make sure you take advantage of them. If we find the percent composition of each element, and this didn't run my notes. So if you add those 2 phosphoruses and uh, 5 oxygens together, add their atomic weights together, which I wrote down on another sheet of paper, so I got to do it real quick. 5 times 16. That's a molecular weight of 141.94. You calculate the percent composition of each element. Percent of phosphorus would be 2 times 30.97. Percent math, part divided by total. 141.94. And and multiply it by 100 to make it a percent. That gives you 43.6%. which matches the percentage given in the problem. So if the percent composition of your formula matches the percents given to you, then odds are you got the question right, or you answered correctly, whatever. So there you go. There's percent composition. All right, so next up, for General 2, we're going to talk a little bit about reaction rates. So for the most common way to calculate a reaction rate is to divide the concentration, the change in concentration, over the change in time. But how you determine the overall rate of the reaction is going to vary depending on the stoichiometry of the reaction. So for example, let's say, wrong page. No. Right, let's say you got, look at the reaction between peroxide decomposing to water and oxygen. So you can measure the rate of the reaction, or whoops, back up there. You can measure the change in concentration of peroxide over time, or you can measure the change in water that's being produced over time, or measure the change in concentration of oxygen over time. And remember, these little brackets here stand for concentration, usually molarity. But the stoichiometry it's not all one-to-one. So notice that every time you produce a water, or back up, man, we'll do oxygen. Every time you produce oxygen, you're producing 2 waters. So if for every 2 waters, you're only getting 1 oxygen. So in other words, the rate of oxygen that's being produced is only half of the rate of water being produced. Again, for every 2 you're producing, you're only producing 1. So one way to show that mathematically is, again, we can say the rate of oxygen, which is change in concentration over change in time, that's half of water's rate. It's change in concentration over change in time. And if you compare, oxygen to peroxide, same thing. For every 2 peroxides that you're reacting or decomposing, whatever, you're only producing 1 oxygen. So the rate of oxygen that you produce is also equal to half the rate of peroxide that you're losing. Although with reactants, we usually put a little negative sign in front of our change, because remember, change is usually final minus initial. So if something is reacting, its net change, final minus initial, is going to be a negative value. And for reaction rates, you want to keep everything a positive value. So it's basically a little bit of housekeeping, if anything. We're just trying to make this change, which is usually negative, make it a positive number. So when you're talking about the rate of this reaction, you don't want to have to be as nitpicky as saying, well, the rate is this amount when you're measuring oxygen, or it's this amount if you're measuring these other things. You just want to say this reaction is going this fast. Right. So the way we do that is, or the way we factor in the stoichiometry, we kind of have started to do already. For any reaction, where A plus B produces C and D, the overall rate of that reaction is going to equal, or you can be calculated by measuring the change in concentration of each substance. Although again, we'll put a negative sign if it's a reactant. Let's see. But you factor in the stoichiometry by taking each one of those and basically dividing by the coefficient. So let's say, for example, that, where's my example? Say you're producing water at a rate of 0.56 molar per second. The overall rate, we can get by, applying this little formula to our actual reaction, which I'll write it again right here. So the overall rate will be equal to half of the rate of peroxide being lost, which is equal to half of the rate of water, or equal to oxygen's rate, its change in concentration over time. So here we're given the rate of water. So we're looking at this part of our relationship. So if you pull that out, ignore the other two bits, the rate should equal half of water's rate, which again is 0.56, which gives us 0.28. If you want to figure out the rate of oxygen that's being produced, now we're looking at this. So again, oxygen equals half of water's rate, which is also equal to the rate of the reaction. So again, just looking at this part of our relationship, the rate is equal to just straight equal to the concentration of oxygen lost over time, the rate of, or gained, the rate of oxygen produced, which again should be the same amount, 0.28 molar per second. So that way, using this relationship to define our reaction rate, we don't have to say that the reaction is, well, it's 0.56 if you measure water, but if you measure oxygen, it's 0.28. You can just say that this reaction is 0.28 meters per second. And that's all you got to say. And so we'll look at another example, although I left my note at work because I did this at work. Then I hustled over here to, do this at home. We'll look at another example, and this time we'll use the reaction between nitrogen and hydrogen to give you ammonia. So again, if you look at what's going on, nitrogen, the rate of nitrogen is equal to the change in nitrogen's concentration over time. And again, we just make that a negative, just cosmetic, really, because we just want this change, whatever it is, we're just making it a positive number. Because you can't say that a rate is negative meters per second. It's like saying you're driving negative miles per hour. And the rate of hydrogen would be some change in hydrogen's concentration over time. But the stoichiometry is different. Every time you react one nitrogen, you're going to react 3 hydrogens. So that means for every 3 hydrogens you're reacting, you're only getting 1 nitrogen. So the rate of nitrogen that's reacting is only 1/3 of the rate of H2. Again, for every 3 hydrogens, you're only losing 1 nitrogen. That's 1 is 1/3 of 3. And if you compare nitrogen with ammonia, the rate of ammonia that you're producing is equal to its change in concentration over time. But for every 1 nitrogen you're reacting, you're gaining 2 ammonias. So again, the rate of nitrogen that you're reacting is only half the rate of H2. So you put all these relationships together, you get the overall rate of the reaction is going to equal the change in nitrogen over time, which is equal to 1/3 of hydrogen's rate, which is equal to half the rate of ammonia. So let's say that nitrogen is reacting at a rate of, I don't know, we'll say 0.22 molar per second. If you want to figure out the overall rate, you just look at the first bit. The rate is just equal to the rate of nitrogen that's reacting. So if that's the case, the overall rate is going to be 0.22. If you want to figure out the rate that hydrogen is reacting, if you look at the middle part here, the rate of nitrogen is equal to a third of the rate of hydrogen. So again, we know that this is equal to 0.22. So if we solve for this whole thing here, our hydrogen rate, then it'll be 0.22 times 3, which gives you 0.66. And finally, let's say you want to figure out the rate of ammonia. By this point, we got a couple of options, but if we keep with our original number, 0.22, the rate of nitrogen that's being lost is equal to half the rate of ammonia that you're gaining, which again is equal to 0.22. So I'll lift off my delta. There we go. Here I put it in the wrong place. So the rate of ammonia is equal to 0.22 times 2, which is equal to 0.44. So again, no matter which rate you're looking at, and let's see if I can select this without having to rewrite it. Oops. Select. Oh well, it's too much to select. Oh, sure. That work? Nope. Yeah. All right. So yeah, no matter which one we pick, and the rate is ammonia, disappearing ink, or a third of I don't know what I'm touching to make these lines disappear. It's always got to be something, right? As long as the power didn't go out like it did last week. Yeah, so no matter which one of these you're looking at, if it's equal, whether you measure nitrogen's rate at 2.2 or hydrogen's rate reacting, which is 0.66, or you're reacting ammonia's rate of production of 0.44, no matter which one of these you look at or a measure, you get a rate of 0.22 molar per second. Figured I had to write the unit at least once. Writing all these triangles and brackets was enough. All right. I got lazy and decided not to write the units the whole time. So, we talked about, why we get this relationship, because of the relative differences in stoichiometry. But, when it comes to just finding the relative rates, again, it's just, you get this relationship just by looking at the coefficients. You just divide each substance, reactant, product, and divide it by its coefficient. A coefficient of 3, you divide by 3 or multiply by a third, same difference. Also, too, if you don't like all these brackets, you can do it more algebraically. So like, for example, let's say I'm hitting something. Oh, so well. There we go. So go back. Yeah. Whoops. That's not working. All right. Go back to one of the relationships we looked at before. Or just here. Yeah, we can just let that equal x, this whole thing equal y, this whole thing equals z, or z if you're over the pond. So you got rate equals x, or half a third, or a third of y, whatever, or half of z. So all this stuff here, it's equal to 0.22. Just if it helps, just call that x. And when you're trying to find the rate of hydrogen that's also reacting, just call that z. So just algebraically, 0.22 equals 1/3 z. Z equals 3 times 0.22, which is 0.66. So yeah, if you're not a fan of all the triangles and brackets and having to draw those over and over and over again, you can sub in just x, y's, and z's and kind of do it algebraically. But again, the way we get this whole relationship up here is, we just look at the coefficients. So starting with, you start whatever your reaction is. Your rate is going to be equal to the negative of the rate of each reactant. And again, the negative, you notice we didn't do anything mathematically with it. It was just, technically it's all one big term. Again, it's mainly just to be technically correct because delta is always final minus initial. So we don't want to technically have a negative rate. That would look weird. But you just divide everybody by the coefficient. If it's a 1, you leave it at 1. If the coefficient is 3, you divide it by 3 or multiply it by a third. Again, same difference. A 2, you call that a half. And so from there, no matter which one you measure, you're going to get this actual, you're going to get the rate of the reaction. And some people will note, some people will point out, well, why don't you just measure nitrogen? Because the rate is already equal to whatever nitrogen is. Well, that would be preferred, but sometimes you can't measure the easiest one mathematically. Sometimes it's easier to measure the rate of something with a coefficient of 2 or 3. But again, to get the overall rate, you just divide the rate by the coefficient. So if the coefficient has a 2 in front of it, the overall rate would be divided by 2. All right, so we're going to end. I've actually had one request. This is my first request. It was by email, and I forgot who the student was. But I had a student that wanted to, I don't think he, yeah, I checked. Nobody did on the Hangout page. I have been, I have thought about just making up my own question and pretending that somebody asked it, just to make it look like more people are showing up these initially than they are. Oh, see in the chat room that so-and-so has a question, but I'm afraid there'll be like 1 or 2 people that actually do show up and I don't notice, and they'll tell me to quit my bullshit. So I don't want to do that. Always be truthful, if anything, because it'll be really embarrassing if somebody catches you in a lie. But anyway, somebody asked me to do a homework problem, but I'm not going to do it because the homework is still open and it's for points. I'm not going to do that exact problem. I probably couldn't anyway because it's online homework and the question is algorithmic. It mixes up the numbers. So, but I don't want to do the exact same problem with different numbers anyway. But I will do one from the book that's really, really similar to the one that they're asking about in the homework. So I guess it's time again for what is legally distinguishable from an old show called Picture Pages, which I still haven't got a name for. Image things? I don't know. Play along with Mark? I don't know. Either way. So the question comes from chapter 15 in the book. It's a general 2 question. And it's at the end of the chapter. It's number 22. So you have a reaction with an activation energy of 14.6 kilojoules. At what temperature will the reaction rate be, or at what temperature will the reaction rate be 3 times faster than it was at 22 degrees? All right. So this question uses the Arrhenius equation, or one form of the Arrhenius equation, which would be the natural log of K1 over K2, which would be equal to activation energy EA over R times 1 over T2 minus 1 over T1. So, whoops, hit something. All right, so if you look at this equation, we're given an activation energy, but it's in kilojoules. You have to be careful because the gas constant we use here, that version of the gas constant, is the one with joules. Usually, if you use it, you're talking about anything related to energy. You're going to use the version of the gas constant with the energy term or unit in it. Our joules per mole Kelvin. So we're looking at what temperature will the reaction rate at what temperature will the reaction rate be 3 times faster than it was at 22 degrees? So we'll let T1 equal 22 degrees, but we have to convert it to Kelvin because Kelvin's in our gas constant. T2 is what we're looking for, so our unknown. As for the K's, all we know is that K2 is going to be 3 times faster than K1. But we can take that and plug it into this equation, giving us K1 divided by 3K1. We're just plugging this into here, which would give us the natural log of 1/3. Which is equal to, I keep losing my place, 14.6 kilojoules or 14,600 joules over 8.314 joules per mole Kelvin. So again, watch your units because it drops out. And if plugging everything else, we got 1 over T2 over 1 over 295. That's an ugly 9. So yeah, we do have everything except one variable in this equation. So we just whip out our calculator and start plugging and chugging, solving for the unknown. And assuming I did it right, I'm not going to go through all the algebra here, just for the sake of time. We get a T2 of 362 Kelvin, or if you convert it to Celsius, it should be around 89 degrees Celsius. Yeah. So there you go. That's the end of episode 4, and we actually made it all the way through. Nobody rang the doorbell. Nobody rang the door. I saw the UPS guy drive by a minute ago, but he didn't have to drop anything off today. Power didn't go out yet. Almost done. Let's see, what else screwed up the last 3 weeks? Yeah, I didn't accidentally leave the web page on to futz with me. So there we go. So again, if you're watching this before your exam, good luck. And I'll leave you with this, which I was going to leave you with last week, but the power crapped out on me. So I'll end with this. All right. What the hell is that? Oh. So I'll end with this. I got a gadget. Wait a minute. Oh, never mind. Of course, something had to start beeping. It was my Vita. All right. That's never happened before. I have no idea what that was. Actually, now I want to know what it was. Yeah, nice thing about this mic is I can just walk away and you can still hear me. Oh, it was an alarm. That's right. Forgot I had my calendar crap in there. All right. Anyway, I'll leave you with this. A sodium atom goes into a bar. The bartender looks up and says, "Hey, we only serve cations here." The sodium atom says, "Well, I am a cation." The bartender says, "Are you sure you're a cation?" And the sodium atom says, "Yes, I'm sure I'm a cation, but you know, I'm getting a really racist vibe from this bar. I think I'm going to get my drink somewhere else." And he leaves. Mic drop. Rest in peace, joystick.